What we're going to do today is we're going to talk about sort of carbon and nitrogen in the ocean. And I'm going to focus on modern processes and how they may relate to the understanding the geologic record. And I'll touch upon that a little bit, but mainly it's the focus is on modern processes. We'll start off with carbon, and we'll start off at the base of the food web. And as Jim mentioned, I'll draw parallels with terrestrial plants, the flux of CO2 in and out of the cell, or the plant, and what controls that. Then we'll move into nitrogen. We'll talk about the processes that control inputs, outputs, as well as internal cycling, as well as the isotopic composition of nitrogens in different reservoirs, and what are the processes that control those values. And then we'll move into something that I actually began here in Jim's lab when I was on that sabbatical in 2005, and that's using isotopic compositions of individual amino acids to learn something about the ecology of organisms. And it'll be an introduction. If it's too much of an overlap with what Seth did, say, raise your hand and say, Seth talked about that already. Let's move on a little bit. But I'll show you some of the basic understanding behind those processes, as well as some examples of some things that are in the literature that we've been working on, as well as others. Okay. The motivation for understanding carbon isotope variations in marine plants is really to understand how potentially carbon dioxide levels in the ocean have changed through time. When you think about the flux of CO2 into a plant, the flux into the cell is going to be governed by the concentration of CO2. So early on it was proposed that potentially the carbon isotopic composition of marine organic matter through time could be a proxy for CO2 variations through time. And that would be great because it would extend the records of CO2 concentration, or atmospheric PCO2, beyond what we have in ice cores, which is roughly about 1 million years. And it could extend it back through geologic time. We'll start off with this slide that Jim showed you. And it is the work of Graham Farquhar, as well as many others. And well, it shows discrimination is a function of some transport, an isotope effect associated with diffusion of CO2 in air, and that's about 4.4 per mil, and an isotope effect associated with carbon fixation. So in C3 plants, it's RUBP carboxylase, and that's about 27 per mil. And then Jim showed this figure too, where he related carbon isotope fractionation to the internal to external CO2 concentration. And again, that's what's controlling the flux in and the flux out of CO2 into the cell and out of the cell. And what's driving this CI to CA ratio in terrestrial plants? Stomatal conductance, yeah. And why would a plant open and close its stoma? Come on. Protect itself from losing moisture. Yes, especially in Salt Lake City today. It's going to be dry, it's going to be hot. You can walk up to those plants and look, and we're going to see their stomata close. Well, maybe not. But we could analyze their isotopic composition. We could probably see a relationship between fractionation and internal-external CO2 concentration. Many times, experiments in the laboratory, we can measure the CI-CA ratio, and we can make those determinations. This is a chamber in which the carbon isotopic composition of CO2 is measured in the air moving into the chamber as well as out of the chamber. You can derive from that the isotope fractionation. You can change the humidity and temperature in there, and you get a nice system, nice experimental system. Can we measure the internal concentration of CO2 in a marine, inside a marine microalga? Nah, we can't do that. So, but we can draw upon this theory. And so, I'm a geologist by training, and in the geologic literature, we don't look at big deltas. Big deltas are basically the difference between two delta values. I deal with epsilon values. So this is the Farquhar equation translated into geospeak. So epsilon P is basically the difference between the isotopic composition of aqueous CO2, marine, microalgae, or C3 plants. They use RUBP carboxylase, they fix CO2. So the difference between the isotopic composition of CO2 and plant organic matter. Again, we've got a transport term, a fixation term, internal, external CO2. And again, we can't measure the concentration of CO2 within a plant. So what we can do is we can grow plants and we can measure how fast they grow. If you measure how fast they grow, it's logical to assume that the rate of carbon fixation is proportional, the rate of growth. It grows faster, it fixes more carbon, so the internal demand within the cell will be greater. So what does that do? That controls the flux of CO2 out of the cell. So in essence, we can parameterize growth rate as the net cellular CO2 flux. We can say that the external concentration of CO2 times some rate constant, now, whatever that is in terms of how fast CO2 can diffuse or move across the cellular membrane, minus the flux out has got to be the growth rate. So there's what's the fate of CO2 within a cell? Either it gets fixed or it leaks out. The rate at which it gets fixed is proportional to the rate of growth here. So we can solve for CI here, and we can substitute it into this equation, and we get something that's messy, but you know what? That's linear. That's a linear equation. We would expect a linear relationship between epsilon P, again, the difference between the isotopic composition of aqueous CO2 and plant organic matter, and growth rate divided by CO2. It's basically CI to CA ratio, or CI to CE ratio. And if these two rate constants are at least approximately equal, and again, that's a rate constant for CO2 across the membrane going in, across the membrane going out, it's logical that they would be pretty close to one another. And in that case, as we go to infinitely low growth rates or infinitely high CO2, external CO2 concentrations, we would expect fractionation to maximize. Why? Well, okay, if this goes to 0, that drops out, that cancel each other, and epsilon P will go to epsilon F. So, okay, we did some experiments, and it was great. One day we collected these data. It took a few weeks. What we did is we grew Phaeodactylum tricornutum. It's a laboratory rat. It's a laboratory weed. It's a pinnate diatom. And it just grows well in culture. And we grew it in a chemostat culture. In a chemostat culture, I'll show you a diagram of what one of those looks like. We can control the growth rate. So what we did is we picked different growth rates, we set different CO2 levels, and so we controlled growth rate, we controlled CO2 concentration, and we measured epsilon P. We measured the difference between the isotopic composition of molecular CO2 in the culture and the organic matter here. And what do we get? Well, that looks like a pretty nice linear relationship. So it begins to fit what the expectation of that model is. And now at infinitely low growth rate or infinitely high CO2 concentrations, we drive this close to the origin, we get a value that is pretty close to what we would expect for fractionation of rubisco as well as all carbon-fixing enzymes within this plant. So we're kind of happy with that. We grew these at a 12-12 light dark as well as continuous light. Okay, so happy with that result. We thought, okay, we can't base the geologic history of atmospheric CO2 based on a laboratory weed. So what would you do if you found this result? You go out and get other species and grow them the same way, right? Yeah, so we did. And that's the relationship we got. So a little bit confusing, but let's sit back and let's look at the requirements for that model. All right. It's a linear relationship with an intercept here that is pretty close to what we would expect for carbon fixing enzymes. And we got one here that's not, but we'll come back to that. Let's focus on these three species, which are all eukaryotes. This is a prokaryote. Phaeodactylum tricornutum, again, we got a nice linear relationship. Emiliani huxleyi, this is a haptophyte that makes these peculiar carbonate plates, and it puts it on the outside of the cell. So we have both calcifying strain and a naked strain, non-calcifying. And the relationship is still linear, and the data fall within, agreement with one another. And then there's Porosira glacialis. This is a centric diatom. A centric diatom kind of looks like a pillbox. And again, we've got a nice linear relationship, but those slopes are very different. At the same conditions of growth in CO2 for Porosira glacialis and Phaeodactylum tricornutum, the fractionation can be different by 20 per mil. Is that a lot? Yeah, it's a lot. If we wanted to predict CO2 concentrations through time based on the carbon isotopic composition of marine algae, we wouldn't be able to do it with 20 per mil variation for two plants growing on basically the same conditions. So why do you think those slopes are so different? Okay, so...
Are the growth rates comparable?
Yeah, we set the growth rates. So growth over CO2. Oh, you mean overall growth rates? Yeah, they were pretty similar. This Porosira glacialis is a diatom found in the cold Southern Ocean. So its maximum growth rate wasn't the same as that laboratory weed, but pretty close, but under similar conditions of growth. We can see what the difference is. What else might control the flux of CO2 into and out of a cell? All right, think about the morphology of this pennate diatom versus the morphology of a pillbox. Surface area to volume. Yeah, their cell geometry is different. Okay. Let's think about that. We have CO2 external to the cell. There's a flux in, there's a flux out. Some of it gets fixed. All right, rate of fixation is proportional rate of growth. The isotope fractionation associated with CO2 diffusion in water is less because there's some interaction with water. It's about a per mil. And then the isotope effect associated with fixation, well, all carbon fixing enzymes appears to be around 25 per mil, but a lot. Okay, so we know CO2 concentration. If you increase CO2 concentrations, you're going to increase the flux in. If you increase the rate of fixation, you're going to control the internal CO2 concentration, but also cell geometry. If you got something that has a very, very large surface area and a small volume, there's more area for CO2 to flux in, and volume is really carbon per cell, and growth is the rate of carbon fixation per cell per carbon. So it's controlling the amount of carbon within that cell. Also, calcification. During calcification, there's production of CO2. That's a byproduct. I mean, you just write the reaction. CO2 is produced. In the case of Emiliani huxleyi under the conditions that we grew, it didn't appear that CO2 had an influence on carbon isotope fractionation, but it could. It could. Okay, so let's factor in surface area to volume. When we do that for those eukaryotic plants, that you see that it explains 70% of the variation. And that's just simply microscopically looking at it and going, okay, this is what the cell dimensions are. let's calculate, let's go back to geometry and calculate surface area and volume, and that's the relationship that we get. So let me back up just a moment. Synechococcus, whoa, that's a weird one. It's linear. Well, yeah, I mean, there's no change as a function of growth in CO2. And the intercept here is about 8 or 9 per mil different. 8 or 9 per mil in a carbonate system. Does that remind you of anything? What's that? That's a number that might stick in your head from Howie's lecture. In seawater, what are the forms of inorganic carbon? A hint, aqueous CO2. What else? Bicarbonate and carbonate. What, at the pH of seawater, what is the most abundant form? Bicarbonate. What's the difference in the isotopic composition, carbon isotopic composition between CO2 and bicarbonate? At about 20 degrees, 22 degrees. About 8 or 9 per mil. It turns out that Synechococcus likes to have lots of CO2, and what it does is it kicks out protons and it pumps that charged species into the cell. So what is crossing that cell membrane is not aqueous CO2, it's bicarbonate. And bicarbonate is enriched by 8 or 9 per mil, just the difference here. Had we calculated epsilon p based on the carbon isotopic composition of bicarbonate, it would show this 25 per mil fractionation. But in fact, it does. There are other plants that also do this in the ocean. They evolved when CO2 concentrations were much higher, and today they're lower. Well, we're kind of remedying that, and we're trying to help organisms in the ocean, plants in the ocean grow better by adding more CO2, but they've developed strategies, and one of them is to take bicarbonate, which is the most abundant form, dehydrate it in the cell, and fix that CO2. So that's the story is with Synechococcus. If you were trying to understand CO2 variations through time, you wouldn't pick Synechococcus as your model organism because it doesn't care what external CO2 concentrations, aqueous CO2 concentrations are. It takes up bicarbonate and fixes it. Still fixes it as CO2 though.